So what to do is to make it into 2 steps. Step 1 is to shoot it, well, project it towards the side, the axis that is the biggest, or if you're below the sort of ellipse, like here, you project it towards the side that is the biggest, but until you hit the side, or well, that is the sort of ideal point you project towards, but you never really hit it, so you get to go towards it on that axis by some ratio, and the ratio is the thinness of the ellipse. So it's determined by this sort of simple equation. So take the square root of the absolute value of b minus a divided by b plus a, and if you don't want to bother with the absolute value, you just take the biggest value first, so a minus b divided by a plus b. Like, obviously the order here doesn't matter. And the square root is just there, it just makes it a little bit nicer, but the whole thing will always be between 0 and 1. So it's a ratio of how much you go towards the ellipse as step 1. So if you get, in this case, b is 3 times the size of a, so 3 minus 1, so on, it will become half, so square root of it will be 0.707. So up here we will go this like a half, then 0.7 here, that will be step 1, and then step 2 is to project it towards the center until you hit the ellipse. So this will become the point that is the closest, and you could kind of see it, how like it's what we expect to be the closest point. And down here this is sort of 0.5, and then this is 0.7 or something, and from here to here we would hit the ellipse on this point. So this is pretty much the normal projected from the points, and we would hit these points. So even if we have very extreme cases, one of the extreme cases is if b is equal to a, it's just this what's it called, a circle. It doesn't matter which one is the biggest, well, when they're equal, because we won't project at all, because this value will be 0. So from this to this will be 1, 0, so no projection, and then down completely radially towards the center, and this will be the closest point. It's pretty obvious. Or here, then this will be the closest point, and so on. And if it's as thin as possible, then it will just be a line, and then we would just project completely in towards it until we hit the line. And if it's a line, then it's not really an ellipse anymore. But if it's really thin, then if we have a point up here, then we project towards the axis, and then we get something like maybe 0.8, and then we square root that, and we get somewhere along here maybe, and then we project that down towards the center, we get a point here, and that seems to be about the closest point. Well, when you have a point down here, you project towards the ellipse, not towards the axis, and that should be pretty easy for it to solve mathematically. I mean, it's just you have this sort of x value, this x value, you have these values, the xo, yo, supposed to be an o, and this y value would then be the same as this one, and the x value, you can use the ellipse equation. So you plug in the y, and you have the a and b values, and you get the x value. And then we call this x ellipse or something, and plus the thinness of the ellipse times the xo minus xe. This is when we equate for the first quadrant, the x and y being positive, but it's pretty obvious how to do it otherwise as well. And when you get from here, you will get an x of it's squared, so you get 2 x values, but the other one is obviously here, so on the other side, so it's pretty obvious which one we will pick, the one with the positive value. One will have negative, one will have positive, but otherwise the same magnitude. Then even if you have a point within the ellipse, then instead of projecting in towards the center, you project out towards the ellipse, and you know, some ratio. If it's 0.5, then here, and then you push it out from the center out towards the ellipse, so you will get that point being the closest to that point. So even that works. Then if you have the, let's see, these values on this point we will get, or this point, that we'll then want to sort of project down towards the center, then what we want to get is the angle. So this angle, we call this, whatever this thing stands for, this Greek letter. We have a triangle where this point is this point. We have a y1 and x1, so we get the tangent of the angle is equal to this value, and we don't even need to make the second tangent or a tangent or whatever it's called. We just did the tangent value in itself, and then we can get x and y values of the ellipse by these equations. This is not approximate, this is actually analytically correct how to calculate it. So a and b and the tangent, it's all you need, these three sort of variables, or well, they will be constant at this point.